Today I'm going to have, within the limited time, I'm going to talk about the general constraints on what the emission mechanism could be from these two aspects, from the energetics, which everybody should do, from the from the first second you think about FRBs, and then from the propagation, which is a little more involved. So from as Lorenzo already talked about, there are generally two classes. You can classify one of the classes in the more general way, saying that it's a maser. There are generally two classes of coherent emission as required by FRB at high brightness temperatures. And what happens is that in the maser situation, you have population inversion in an extended or in any medium, basically, you have an extended medium where you have population inversion such that your wave can grow from an initial small amplitude seed. And then another mechanism, those are two general mechanisms. The other mechanism is that you have spatial bunching of your particles within a small volume, small wavelength, smaller than the wavelength, such that there are m particles emitting at the same time, such that the total amplitude goes as n, and the total flux goes as n squared. That's how you get the high flux. So let's go to the energetics. First, there are many ways you can make FRBs. I'm generally considering these two scenarios as the most likely ones. There are other scenarios. So the first one is the emission comes from within the magnetosphere of a neutron star. The second one is that it's from a relativistic outflow, which dissipates energy at large distances, as we already talked about. There are many other options, which I consider as less likely, but they are possible. If you look at the emission, if you want the emission to be within the magnetosphere of a neutron star, you need to satisfy the energetics such that your wave energy density has to be smaller than your energy available within the magnetosphere, which constrains your radius of emission. It has to be close enough within to the surface of a neutron star within about tens to 100 neutron star radii. And from that, you can immediately get this hierarchy situation where the plasma frequency is much higher than the wave frequency, and the cyclotron frequency is even higher. There is a many orders of magnitude hierarchy in these three frequencies. Okay, these will have implications on all sorts of masers that could occur within the neutron star magnetosphere. In the other scenario, in order to satisfy the time scales of FRBs, you need to invoke some Lorentz factor that is significantly larger than 1, such that you can have dissipation at large distances while keeping the duration short. Okay, so looking at this, it's a busy plot, but looking at this single scenario where the emission is within the magnetosphere, what you see is that due to this hierarchy, one can easily go through the maser mechanisms that have been proposed for the pulsar radio emission many, many decades ago. You can go through those. There are many other proposals. Those are just 3 of them I selected as the so-called most likely ones. But you can find that they all require fine-tuning. Let's say take a look at the curvature maser situation, where a lot of people have worked on, including Roger. The curved magnetic field cannot be confined in a plane. It has to have torsion, out-of-plane torsion. Even in that scenario, the maser cone is within 1/gamma squared tiny cone. That amount of fine-tuning you need in order to generate FRBs. You need all B fields to be parallel. There are lots of other fine-tunings that you need in order for other maser mechanisms to work. So this is another mechanism for the so-called antenna mechanism, where you have charge bunches moving along field lines, emitting curvature radiation. So a very simple calculation that one can do is that in those situations, those are like antennas. Because antennas, you have oscillating currents. The actual power is not from kinetic energy of particles. It's from the EMF. It's from the source which is supplying the current. Basically, it comes from an electric field, which is parallel to the B field, driving the motion of the charge bunches. And it can easily show the isotropic equivalent luminosity is roughly of order E squared and the curvature radius squared times C. It's a very simple calculation one can very quickly do, and you can easily generate FRB luminosities given that you have a strong electric field. of course, the current would perturb the B field, which require a much stronger B field to sustain the current. So that's the basics about these two mechanisms. Let's look at the energetics and see what are the constraints. First, because of this curvature emission, one can immediately look at what is the maximum amount of luminosity that you can get, which is one of the constraints. So the maximum luminosity is given by the electric field not being too strong. It cannot be more than about 10% of the quantum critical electric field. At that point, you generate Schrödinger pairs. No more electric field which will be shielded. So you get something like a maximum luminosity of this, and you can look at the dm, which is the distance and fluence plot. That's over there. You can see that there indeed seems to be a lack of those events at high luminosities. So let's look at the relativistic outflow dissipating at large distances. So those are the very general three relations that you would generally expect. So the FRB duration is related to the distance of emission by the Lorentz factor, which is well known. And typical frequency for all sorts of plasma masers, there could be synchrotron, there could be other sorts of plasma masers, is roughly related to the plasma frequency. Given that sigma is order unity, this is of order the cyclotron frequency as well, and multiplied by some boosting of gamma. This is related to the density. And the total energy involved in the system is just given by the total rest mass energy multiplied by gamma squared as they've been shocked. From these three, of course, there are many complications, like there are upstream magnetization one can take into account, and composition, and different types of masers and pre-shock motion, as Andre talked about. You can take all those into account. This would modify this simple relation by of order 10 or a little bit more. Not so much, but this is the general relation that you need. The total energy you need in order to dissipate, in order to have your radius of a dissipation, let's say at 10 to the 13 centimeters, that's the amount of energy you need in order to generate. This has nothing to do with the maser efficiency or whatever. This is the total energy you need, very strongly dependent on the shock radius. And you can see that for FRBs, this is the FRB energy efficiency seems to be low unless your radius of emission is smaller than 10 to the 13 centimeters. And this can be accommodated by magnetar flares, easily accommodated. So those are from the energetics. Those are the conclusions you can get easily. And from the propagation. So first, the propagation within the magnetosphere. Sorry, I'm switching between. Hopefully you're not so confused. So in the magnetosphere, the first thing you notice is that the total number of particles, the total rest mass energy of all Goldreich-Julian density and some multiplicity factor is small compared to the FRB energy. You conclude that the FRB waves are so strong, they are like an elephant running into flies. The flies are not going to stop the FRB radiation. So they basically cannot absorb FRBs within the magnetosphere. What happens in the magnetosphere is that the polarization is modified. So this is a very simple. It has been worked out in the rotating vector model in the past. What we have done is that we accommodate the strong wave effect. FRBs are strong waves such that this Lorenzo defined this as a Wigler parameter. This nonlinearity parameter is much greater than 1 within the magnetosphere for FRBs. You can take that into account and calculate. So what happens is that electric field stays perpendicular to the local B field all the time and adiabatically walks until the freeze-out radius, where the plasma density is low enough such that the plasma is virtually vacuum. So the polarization vector freezes out at this freeze-out radius, which typically is much less than the light cylinder radius and much larger than the neutron star size. From that, you conclude that the polarization is perpendicular to the magnetic dipole moment, which is periodically rotating around the spin act. And also there's a small amount of Faraday rotation in the magnetosphere as well, which for 121102, this is too small to be observed. But for other cases, there could be some implication. So for the relativistic outflow scenario, what kind of propagation effects you would expect? So this is the general sketch on what the outflow scenario would do. You have a shock. This is a shock running into the pre-shock medium. And after the shock, there could be population inversion in the shocked medium or at the shock, as in different scenarios. In all scenarios, the FRB radiation comes ahead of the shock because it's propagating at speed of light. So the pre-shock electrons would see a narrow beam of strong FRB waves within a narrow cone of 1 over gamma squared. Gamma can be properly defined either as the shock Lorentz factor or the post-shock Lorentz factor, depending on the scenario. But that's what you would expect. What happens is that there will be induced Compton scattering. What happens, so there's a little bit detail of what induced Compton scattering do, is that if you have radiation given in one direction, it can get scattered into another direction if there are already photons. If the photon occupation number defined as follows, well known, which has been worked out by previous people, a lot of previous works, the probability of being scattered into this cone is much higher if n is much greater than 1. For FRBs, a number to know is that this is of order 10 to the 35. So it's a huge amount of scattering. Of course, you have to subtract the back scattering. There is a little bit difference between forward scattering and back scattering into this cone. Depending on the electron recoil, one can take that into account. So the final outcome is that because the radiation is beamed, they put a momentum kick onto the pre-shock electrons such that electrons are accelerated to a Lorentz factor of order gamma. And that may shut off the major emission. So we require that the acceleration is not so. Previously, we require there is an induced Compton optical depth, but this constraint turns out to be much stronger, as we recently found out. This constrains that the shock radius has to be greater than something like 10 to the 13 centimeters, as shown here. So this is the Lorentz factor of the jet running into the medium as a function. The kinetic power as a function of shock radius. You can see that only this parameter space is allowed due to the constraint by acceleration. So from that, as I previously calculated, you can easily conclude, taking into account all kind of complexities, as I mentioned, you get the conclusion that the energy has to be greater than 10 to the 46 ergs for typical FRBs of this. Those are brighter ones. Those are brighter than the repeating FRBs, but still typical. From those, you conclude that the efficiency must be quite low, cannot be 10 to the minus 3. I still have a little bit time. Let me go a little bit. I have 2 more minutes. So those are the summary, which I will come back. So there are also some strong wave effects that one might expect, but at distance much larger than 10 to the 14 centimeters. At those radius, let's say 10 to the 17 radius, now I'm considering a very bright FRB, just to emphasize the strong wave effects. The nonlinearity parameter is not so much less than 1, it's 10 to the minus 2, meaning that electrons are oscillating at speed, 1% of speed of light. What are the implications? The first implication is that the rest mass of electrons is modified by of order 10 to minus 4. So that modifies the dm and rm as well. So there will be such a small modulation, luminosity-dependent modulation. If you got a repeater, for different luminosities, you will see such a very tiny, which is predicted has never been seen, of modulation that you may expect. Also from the 121102, I kind of, from Laura's talk, one can roughly estimate if this dm and the rm change are due to the same cloud. You can do the ratio. Mm-hmm.
Dimensions are wrong.
I mean, yeah. I'm sorry, but per year. Per year, you do the ratio of these two, you get a magnetic field, 10 milligauss, quite high, but not crazy, I would say. And from the Rm, which is 10 to the 5, divide by this, you get a local dm. So there is some amount of local dm. So the amount of, you expect 10 to minus 3 of modulation due to strong wave effects. So another thing that you would expect, this is a very simple thing, is that the free absorption is suppressed because electrons now are oscillating at speed much higher than their thermal speed. Let's say for 10 to the 4 Kelvin, your thermal speed is 10 to the 4 kilometers per second. Right now, for strong wave effects, the oscillating speed can be much higher than your thermal speed. So you see there's a strong suppression which roughly goes as a to the minus 3 of the free absorption. This is oh, I'm running out of time. I'm sorry. So this is just to show for a given flux or a given luminosity, you see that as you go to lower and lower frequencies, initially the optical depth increases and then the optical depth drops. So that is the. So I'm gonna go to the summary slide and leave for questions.